All right, so we're moving on to chapter 13, which is all about alcohols. We've already seen quite a few reactions with alcohols, so a lot of this will be review, but we'll learn a few new reactions. One thing I'm going to ask you guys to do is to review naming and nomenclature on your own at home. I've included a link for a Khan Academy video on nomenclature, but I don't want to waste lecture time going over basic naming. So please make sure you read that at home, and then there's a couple questions on the pod that deal with naming as well. But let's take a brief minute to review the acidity properties of alcohols. And let's take the most classic alcohol, or water. And in fact, I'm going to draw two water molecules. And if we think about this, right, we said that all the way back in 161 that water is in equilibrium with other water molecules, right? You guys remember Kw? So in this case, one water molecule can go over, deprotonate another water molecule, and you can create hydroxide and hydronium ions. And we said that the pK of water is about what? Because 15.7. Yeah, you guys are close. Its pKa is about 15.7. And the pKa of hydronium is about negative 1.7. So we know that the hydronium ion is a much more powerful acid, which is why I have the equilibrium arrow. Whoop, I've actually got them flipped. The equilibrium arrow should strongly favor the water side as opposed to the hydronium ion side. The same is true with alcohols. They have very similar pH values or pKa values. Where if you have an alcohol and some sort of base like water around, you again would have this equilibrium where you would make hydronium. However, you would also make an alkoxide. An alkoxide is really similar to hydroxide, but you just have some sort of carbon group attached. What does the R mean in just general organic chemistry terms?
Carbon or hydrogen.
It's just any carbon atom, right? So it could be any sort of carbon group. This is a generic alcohol. Typically, alcohols have pKa's from anywhere from about 9 to 18. Why do you think the range is so big?
Depending on how many groups you have coming off.
Yeah, so maybe the number of carbons coming off. What else could stabilize an alkoxide? Resonance, induction, right? So there's a lot of features we talked about first term that could stabilize the alkoxide and make the alcohol a lot more acidic. Let's take a look at one really basic example. And this one's going to show up a lot throughout the year. Let's say we've got this compound. This is phenol, and its conjugate base is called phenoxide. Why is this so stable? Yeah, exactly. So phenoxide is resonance stabilized. And because of that, this has a pKa in the ballpark of about 10.
You swap your equilibrium?
No, in this case, pKa of 10, it's still not super great because if we think about the conjugate acid in equilibrium, it's still got a pKa of negative 1.7, right? So it's still going to push it mainly towards the neutral side of the equilibrium, not the phenoxide side. All right, so alkoxides and phenoxides are common reagents. We use them a lot as bases, right? So we've used methoxide and ethoxide and terbutoxide as strong bases. Oftentimes, chemists actually make these in lab. So let's discuss how we can make some really generic alkoxides. So let's say, for example, I've got ethanol, and I want to form ethoxide, specifically sodium ethoxide. What's a reagent that I could use?
Sodium.
I heard it in the back. What was that? Strong base.
So sodium hydride.
Yeah, sodium hydride. So if we do sodium hydride, right, we could have Na plus and H minus. And in first term, I told you guys that this is a really nice base because the byproduct is just going to bubble out of solution. So you make H2 gas. This is a really easy way to make an alkoxide. This could be your nucleophile, it could be your base. You can use it for whatever you want. Another way to do this is by using some sort of metal. Specifically, you could use potassium, sodium, or lithium. So I'll write lithium, sodium, or potassium. Which one's going to be the most reactive? Potassium, definitely. So lithium, if you've ever seen it, you can throw it in water and it kind of skips across. Sodium will actually catch fire a little bit. Potassium is more of a small explosion. So typically chemists prefer to use sodium because it's kind of this middle ground where you don't have to worry about blowing yourself up and it's relatively easy to handle. There's actually a cool video online. I'll see if I can find it later and post it. But after World War II, the US government disposed of literally tons of elemental sodium in a lake. It's probably not the most environmentally friendly way to get rid of sodium, but it was a nice big explosion that they got out of it. So for example, your alkoxide, the cation could be potassium, sodium, or lithium. And in this case, you're only going to make half an equivalent of H2 gas. This mechanism is actually more of a radical mechanism, and we're not going to cover it because it's not covered in the book. So for example, if you wanted to make tert butoxide, oftentimes what you do is just get a big flask of tert butanol, and you would just throw in some potassium metal. Potassium is this really dull looking metal. You can cut it with a butter knife and just flake off the potassium into your round bottom flask with your tert butanol. And when you do this, you can create your alkoxide. And you may have noticed in the textbook that oftentimes when you see these reaction arrows where you use a strong alkoxide base, that it's shown as TBUOK and TBUOH. Right? You guys saw that? Why do you think they're showing the TBUOH on the bottom?
There's still some remaining.
Yeah, usually you don't throw in an excess of potassium because it can be dangerous, but you do have residual tert butanol around. So oftentimes these are done in combos, so the alkoxide's got its corresponding alcohol as the solvent, right? All right, so let's review a little bit of how we can prepare alcohols. And most of this is just review from the exam. Or last term even. So let's say we've got one bromopropane, and I want to make propanol. What reagent should I use? What do you guys think? Yeah, absolutely. If we look at this, right, I'd say this is our primary electrophile. Is this going to be an SN1 or SN2 reaction? SN2. So we'd want a strong nucleophile. So something like sodium hydroxide would work well. We could say, all right, if we throw in sodium hydroxide, this would be an SN2 mechanism, and we can make an alcohol this way. Pretty easy and straightforward. The other method that we learned first term works on more hindered substrates. Do we need to use sodium hydroxide for this next reaction? What's the problem if we use sodium hydroxide?
The elimination.
We get elimination reactions. So in this one, we do not want to use sodium hydroxide. What would be a better reagent? If you don't want a strong base, just tone it down a little, right? So we could just throw water at this. And this would do our E1 mechanism and SN1. How could we favor SN1 over E1?
Low temperature.
Yeah, run it at lower temperature, right? If we crank up the heat, we'll favor E1, but if we keep that heat down a little, we can try to favor SN1 formation. So we know that tertiary electrophiles will do SN1 and E1, and in fact, we don't want to use a strong nucleophile in a lot of these situations because they'll do E2 chemistry instead of your substitution chemistry. All right, so that's our review from term 1. Let's review a little bit from chapter 9 and 10, and these were our addition reactions. And with addition reactions, we said we can have a generic alkene. And I want you guys to help me fill in the missing arrows here. And for the first one, I want an alcohol coming off the more substituted carbon. Same with the second. And then the third, I want it off the less substituted carbon. So I'll give you guys a minute to see if you can come up with 3 different ways of making an alcohol from this alkene. And then give me a thumbs up if you immediately got all 3 of them or if you're done. In your head? All right, let's do the first one. What's the easiest way to make the top alcohol up here? Yeah, just acid and water, right? So you could do sulfuric acid or phosphoric acid, and then just a lot of water. In this case, we want to use Le Chatelier's principle to our advantage and push the reaction to the alcohol side. So that's an easy way. What's another way? Oxymercuration, demercuration, exactly. So that was the method we saw on the exam. So HgOAC2, water, and then what do we have in step 2?
Sodium borohydride.
Yeah, sodium borohydride, NaBH4. This reagent's going to come back a lot in this chapter. It's a really useful reagent for making alcohols. And then what about the last one? What if we want the anti-Markovnikov alcohol? Yeah, hydroboration oxidation. So we'd have BH3, THF, sodium hydroxide, and hydrogen peroxide. So make sure you've got these down cold, because at this point we're going to assume that you guys know them all. Let's do the same thing with diols. Actually, I'm going to give myself a little bit more room here. So let's assume we want to make a couple different diols. We've got a couple ways of making our syndiol, which in this case is meso. And then we've got another way of making our antidiol. So I'll write plus En over here. So let's see if we can remember the 3 different ways for making these alcohols. Then give me a thumbs up if you've got them identified already. All right, so let's do the syndial ones first. What's one way of making a syndial? Does anybody want to help me? Potassium permanganate. Okay, so KMNO4. What were the other reagents? Yep, sodium hydroxide. And you have to run it cold. Does anybody know why you have to run it cold? Because the book says so. If you run this hot, it will actually split an alkene into 2 different carboxylic acids. So you have to be very, very careful to run this cold, or else it will over-oxidize it to 2 carboxylic acids. All right, what's the other way?
Osmium.
So osmium tetroxide, so OSO4, and then step 2 was what? And water. There we go. So you've got 2 options. What was the problem again with the osmium tetroxide? Yeah, it'll make you go blind. So if you can use KMNO4 and it won't fry your molecule, it's oftentimes a good option. But if you're stuck and you have no better route, then you've got to go with the more dangerous osmium reagent. All right, how about antidiols? Yeah, MCPBA. This is going to come back next chapter a lot. Does anybody remember what MCPBA stands for?
Metachloro.
Yeah, it's metachloroperoxybenzoic acid. So any peroxy acid will work in this step. So if you see on sapling, peroxy acid or I'm trying to remember the one they use. They use peroxyacetic acid, I think, pretty regularly, but any peroxy acid will work. And then step 2, we just need dilute acid. So you could have a drop of sulfuric acid and water, and that will ring open it into the antidiol. Does that make sense? All right, so now we're going to do a time trip back to redox chemistry, because I'm sure you guys love redox chemistry. How many of you guys have covered redox chemistry at least 3 times at TCC? I was talking to somebody the other day, and they were like, we covered redox in Chem 110, 121, and then in the 160 series. I don't know if that's true or not, but we're going to do it again. All right. So redox always involves reduction and oxidation. And I'm going to put my own organic chemistry spin on this, but what does it mean when a reduction occurs?
Reduction is gain of electrons.
Yeah, it gains electrons. And oxidation
Loss of electrons.
is losing electrons. So you can use oil rig or Leo goes Gur, whichever funny acronym you want. All right. However, with organic molecules, things get a little bit trickier. So we're going to talk about this in relation to formal charge. We spent most of the last term, drilling in formal charge. However, oxidation state is equally as important. So let's do this. I'm going to give you guys a compound. First one is methanol, and I'll show you guys the trick for determining the oxidation state. What I do is I draw the most basic Lewis dot structure imaginable. I don't even draw solid bonds anymore. I draw individual electrons. So for example, with methanol, you could say, all right, here's my covalent bond to oxygen. I've got a covalent bond to 3 hydrogens. And the oxygen's covalently bound to another oxygen, right? Or sorry, hydrogen. Holy cow. All right, so super old school. And then the trick with oxidation state is that the more electronegative atom gets all of the electrons. When determining oxidation number. And then the other thing I wanted to note is if it's a tie, then share. Okay, so let's do this with our methanol that we've got up there. And I've got this electronegativity table to help us out. So when we're looking at the carbon-hydrogen bond, what's more electronegative? Yeah, carbon is 2.5, hydrogen's 2.1, so carbon's going to be more electronegative. It's going to take both electrons in that covalent set, right? And then what about between carbon and oxygen? Oxygen. So in this case, carbon's going to get the electrons that it's sharing with oxygen, with hydrogen, but the oxygen's going to steal the other one. So now what I do is I take my valence number minus my circled electrons, and this gives me my oxidation number. So if we do it for methanol, valence number for carbon is normally what? Oh, come on, guys. 4. If you look at the columns in the periodic table, right, it's group 4. And then we've got how many circled electrons? 6. So its oxidation number is going to be -2. This doesn't immediately tell us a lot unless we're comparing it to another molecule, but we'll talk about that in a second. Let's do a couple of examples down here. Okay, so for this example, I'm going to say, all right, we're going from an alkene to an alkane. I want you to determine the oxidation number for each carbon and determine whether or not this reaction is an oxidation reaction or a reduction reaction and how many electrons were transferred in this process. But before we do that, what reagent do we need?
H2, or just H2.
H2 and like palladium, platinum, something like that. All right, so now we're ready to go. We can take a look at the oxidation number for the carbons and determine whether or not it's a redox reaction. And I'll get us started too. Is this how you guys were taught in 161 or 162? No? Okay. You just drew lines?
They were kind of like rules, like an oxygen's always a -2.
Yeah.
Formal chart that you went to, and you try to make them work algebraically.
I remember learning it that way, and I never liked that because it just felt like a list of rules I had to memorize. So hopefully this way is a little bit more intuitive. All right, so let's determine what's more electronegative, carbon or hydrogen? Carbon. What's more electronegative, carbon or carbon?
Yes.
Carbon. All right, so we said if there's a tie, you're going to split these, right? However, carbon's more electronegative than the hydrogen. So let's do that same thing. So its valence number, which we said is 4, minus 246. That means our oxidation number is -2. What about the other carbon?
4 minus.
It's the same, right? So each carbon's -2.
Oh, the other carbon there.
No, I'm saying the other carbon in the alkene.
I thought you meant the
Yeah.
other side.
All right, so let's do the next one. Same thing, it's a tie. And we would say, all right, 4 minus 2, 4, 6, 7. That would be -3. Wait, did I? Okay. I'm not even trusting my basic subtraction right now. All right, so is this a reduction or an oxidation? If we look at this, we gained an electron, and it's a reduction. That is why when we refer to reduction, people get confused and they're like, what do you mean reduction? You're adding hydrogens. Shouldn't it be an addition or an oxidation or something not reduction-like? And it's like, no, the reduction is referring to the electron count for the carbon. So in this case, anytime you're converting a triple bond to a single bond or a double bond to a single bond, that's referred to as a reduction reaction. You guys want to try another one? A little bit different? All right, let's mix this one up. So CO2 to methanol, I want you guys to help me determine whether or not the carbon is being oxidized or reduced and how many electrons are being transferred in this process. We don't know the reagents that are used. However, this is a catalytic transformation. Also, if you want to become a self-made billionaire overnight, figure out how to do this cheaply and efficiently. Oh. I'll draw in all of my electrons here. So what's the oxidation number for carbon and CO2? Positive 4. This is kind of an odd example, right? Because each of the oxygens is more electronegative than the carbon. So we would do 4 minus 0, which would just be positive 4. And then with methanol, we said it's going to be what again?
Negative.
Yep, so 4 minus 6 equals negative 2. So in this case, this thing's really changing a lot. In this case, we're gaining how many electrons? 6. So in order to convert CO2 to methanol, you have to really, really, really push on it to reduce it. So this is a 6 electron reduction. This is also why it is so challenging to take CO2 from the atmosphere and actually convert it into a useful fuel like methanol. It's a pretty intense transformation. If you've read any of the recent news articles, there were a few groups earlier this year figuring out how to do this a lot more efficiently. And that's the big push right now, is if we can figure out how to sequester all the CO2 in the atmosphere into methanol. Methanol is used in everything from fuels for planes and cars, all the way down to making plastics. So theoretically, if we could pull all the CO2 out of our atmosphere, we would mitigate a lot of the climate change problems that we're facing today. Does that make sense? All right, so we're going to finish off talking about some reduction reactions. And there's a handful that are really common. So we're going to talk about aldehydes and ketones at first. So let's take a look at just a simple ketone. And let's say I want to convert it to an alcohol, right? We've seen double bonds go to single bonds before already, right? What reagents were we using to reduce alkenes to alkanes? Yeah, we just use H2 and palladium, platinum, or nickel. Any one of those would work. However, I'm going to make a note in here, and that is that it is not common. It requires really high pressure. It requires much higher pressure than a normal alkene, and so you typically don't see these reactions done unless there's really no other alternate. So that brings us to different classes of reagents that can accomplish the same transformation. So let's take this ketone, keep it consistent, and we'll convert it to an alcohol. However, we're going to use NaBH4. What was that called again? Yeah, sodium borohydride. And we can run this reaction in an alcohol solvent. So in this case, if we look at the oxidation state for this carbon, what is it going to be?
Plus 2.
2 is 2.
4 minus 2 would be positive 2. And then over here, if we look at this, what's the oxidation number now going to be?
Plus 2. Plus 0.
There's a hydrogen, so. So 1 is 2.
Ah, don't forget about the hydrogen. So it would be 4 minus what?
4.
4. So in this case, you can tell we're gaining 2 electrons. And this is a really simple way of converting a ketone to a secondary alcohol, right? So let's make a note of that. You can make a secondary alcohol with sodium borohydride. All right, let's say we want to make a primary alcohol, though. Oop. We can still use sodium borohydride, but I want you guys to help me predict the starting material. What would our starting material be if we want to make ethanol? Ah, an aldehyde, right? Because if we look at this, right, we've got a hydrogen here. So we could just say, you know, what if we had this aldehyde and we reduce it and we add in that hydrogen again? It's still going to be a 2 electron reduction, but we can now make a primary alcohol this way. All right, let's do the same thing with the tertiary alcohol. What would our starting material need to be? Well, let's take a look at it here, right? So on this one, we essentially added in, I'll draw in a blue hydrogen. In this one, we had that black hydrogen, but we added in a second blue hydrogen. What would our starting material need to be for this one? No, nobody's calling me out on this. What do you guys think? Would it be that? Why not?
Texas.
Because that looks terrible and it makes Jeff sad on the inside. So this reaction will not work. That is one major limitation to this reaction mechanism, is that this is a big fat Texas carbon, and you should never ever draw those. All right, so let's really briefly look at the mechanism. All right, so let's stick with our really basic ketone. And I'm just going to draw in all of our atoms right now with lone pairs. And in this case, we've got sodium borohydride. So it's a boron with 4 hydrogens. I'm just going to color code one as blue. This boron has a negative charge, and the sodium is the countercation. This is referred to as borohydride anion. And it's a really, really powerful reagent in terms of reducing capability. This entire hydrogen is going to attack this carbon because we know this carbon has a strong net dipole towards the oxygen, right? So that carbon really wants a negative charge. And when that hydrogen attacks that carbon, it's also going to kick up electrons onto this oxygen. And now we've got our alkoxide anion. And this alkoxide anion isn't very happy with its negative charge, but if you remember, we've got an alcohol solvent. And so this alkoxide is just going to steal a proton from the solvent, and we're going to end up forming our secondary alcohol. Does that make sense? It's a pretty simple reaction. It's pretty easy to keep track of. All right, when we switch gears to carboxylic acids and esters, we have to kind of amp things up a little bit, but I think we're going to wait till tomorrow to talk about that. So make sure tonight that you guys spend a little bit of time reviewing naming for alcohols. Really the only thing that changes is that the new suffix for alcohols is ol, so OL. And then the other thing, too, is your longest parent chain must contain the alcohol functional group. So make sure you identify that longest carbon chain that has the alcohol. Other than that, I won't have office hours tomorrow. I'll have a meeting in the morning, but you can shoot me an email and I'll try to help you.